Mechanics of Materials and Structures 3M. So as you can see, the last part of Mechanics 3M will be more of the first part of our Mechanics 4M. Okay, but there will be two major components. One is continuum mechanics, which covers elasticity and plasticity, and then we're going to move to finite elements, 2D. So last time in Mechanics 3 we did a skeletal finite elements. Now we're going to move to 2D and 3D. You will have projects, definitely, the same as what we had in Mechanics 3. That will be, if things hasn't changed in Glasgow, it will be 20% per report. If things did not change in Glasgow. So I'm still confirming. There will be also so-called the peer-wise that we did last year, but that will be 5%. It's not anymore 10%. Now, the homework or the assignment or so-called project, you will be independent on that. Okay? So the report is already, or the problem is in Moodle. All of them are in Moodle, so you have to do it independently. Individually, independently. And there are cases of plagiarism last year, of course. They didn't get marked for their reports. Of course, those who also were generous enough to have their reports copied by their classmates were also their marks were also reduced because of that. So if you're generous enough, please don't be. Reason, of course, if you're caught with plagiarism, then you will also be affected. Okay? So that's the problem with being generous, giving your homeworks to your classmates. Okay? 20% each, you will be independent, using Abacus. The problems are all in Moodle. Your lecture notes are also in Moodle. Yes? So I don't really have to print them out. Reason because it's all there, so it's up to you to print them out. Exams. You won't have any more just an A4 sheet. You will have all your notes open. But that doesn't mean that the questions will be a lot easier. Have a look at your lecture notes. A lot of students are asking about, exam questions. All the questions there in your notes are based from the exams. Okay? So it's not because it's open notes that it will make life easier for you. Of course not. Now, any questions so far? So I will be generous today, not checking your attendance, but next week I have to be strict with your attendance. Of course, you know the rules. This is your final year, so you have to be conscientious about it. Any questions so far? So like I said, this will be in two parts. One, continuum mechanics, and the other one will be finite elements. Now, why tensors? Tensors basically is the introduction to continuum mechanics. Take note that we won't be dealing too much with matrices, but we will be dealing with indices, indicial notations. Okay, so try to be familiar with all these indicial notations. Okay? Shall we begin? Well, of course, you have been familiar with the scalars, vectors, and tensors. So to be able to write that in a more simpler term, we can use indicial notations. Of course, we can perform different simple operations such as addition, contraction, you will see later again, differentiation and multiplication, and then of course we have the operators, the gradient, divergence, and curl. Okay, so trying to increase the temperature a bit here. So scalars, very simple, arrow with a direction. Of course, a vector will always have a magnitude and it will always have a direction. Of course, scalars are just magnitudes. They can be distance, speed, mass, energy. Mass is a scalar, but if you have a weight, that will be a vector. Okay, mass is a simple magnitude, weight is a magnitude plus direction. Right. So you also have this, what do you call this one, Cartesian coordinate systems. Instead of sometimes we have x, y, z, you can have them as x1, x2, and x3. Okay, so there are many possibilities of naming your coordinate systems. Okay, so rather than having them as x1 or x, y, and z, we can always have them as x1, x2, and x3. And of course, corresponding to that, there will always be vectors, unit vectors. Okay, E1, E2, and E3. Sometimes we associate the magnitude with the unit vector. Okay, meaning that there's a magnitude and then this one will represent the direction. So for example, you have, say, a magnitude V1 associated with this vector here, unit vector. This one magnitude associated with this one, and this one here associated with this one. You sum them all. I mean, not really literally summing them up, but vector sum. Then you get this vector here. Okay, so this is more like a symbolic representation. Of course, you cannot add them. You cannot add each of these because they are in a different direction. Okay? Of course, we will be looking into vectors into the space later on. So instead of looking at the 3D, we can always simplify our analysis in 3D. Oh, sorry, 2D. So of course, rather than using E1, E2, E3, then we have E1, E2. Okay, so all of these materials is in Mechanics 3. I would think it's also in our Moodle. So if it's not there, I will see to it that I will upload them later. Okay, tensors are generalization of vectors and matrices. There are many ways of writing tensors. Okay, there are many ways in writing tensors. Of course, symbolic, bold letters, and so on. You can use the matrices, or you can use the, sorry, this should be initial notation. Okay, so have a look at this one. Stress is basically a tensor. Force is a vector. Stress is a tensor. Moving on. So of course we have different ranks of scalars, of tensors. We have scalar, vector, and so-called tensor. Normally when we have, if the order is, or the rank is 2 and above, we would usually call them as tensor. But if the rank is 1, we just call them vector. Okay, so normally tensor, although all of these are tensors, scalar, vector, and up, all of them are tensors. We would usually reserve the tensor for rank 2 and up. Others, of course, are scalar and vector. So as you can see, this rank 0 is a scalar, it's just a magnitude. For rank 1 vector, you have a magnitude and direction, of course. As you go up, you have different directions. Okay, so this is just for your information at the moment. Sometimes you will be able to know the rank depending on the number of initial notations. So Kronecker delta, the value is either 1 or 0. So this one is basically a unit rank 2 tensor. Unit meaning 1 or 0. That's the only value of the Kronecker delta. We'll use that later. Don't worry. The benefits of initial notation, Okay, rather than writing them in writing them using matrices. This one is one of the benefit, economy and writing, and then compatibility with computer language. This one is important if you're coding. Writing them in initial notation will be much more convenient. But if you're not so coding this, then this second importance here is not really important to you. So basically, it's just the economy of writing. Rather than, say, writing the stress sigma ij into a 3x3, 6x6, or 9x9 matrix, then you can simply write them as sigma ij. So that's the economy of writing. This is what I meant. So a strain is a tensor, rank 2. Epsilon ij is the same as stress. So instead of writing them in this manner, then you can simply write them in this manner here. So economy of writing. Sometimes when you operate on these values, it's even more convenient rather than using the matrix. Okay. Also, have a look at the symmetry and antisymmetry of these tensors here. Some of these we will be discussing as we go on, but they exist. Okay. Especially the stress tensor, they are symmetric, while the strain tensor, they are antisymmetric. Of course, we will be deriving that later. This one is a simple overview of what to expect from mechanics of materials or mechanics of solids and structures. Initial notation, of course, again, the summation rule. Okay? If you have repeated indices, then this one is a summation. Okay? Repeated index, summation. Don't worry, we're going to apply all of these later. You'll like it. Right. Free indices. These are terms, we're just defining terms at the moment. We're just defining terms. It's really important that when you're learning a language, you have to have definitions. So at the moment, we're just coming up with definitions. So as you can see, we have free index and dummy index. Okay, so free index meaning this one will be independent of free, ij, no repetition, I and j are free index. Okay, at the moment just accept. We will be having more examples for you to understand. A dummy index, for example, this one here. Okay, if it's repeated, normally it is a dummy index. It can represent any letter. That's the meaning of a dummy index. So it can be represented by JJ or II, but this one is rather fixed at the moment. That is your free index and a dummy index. Okay, so at the moment, just try to accept there are free indices and dummy indices within an initial notation. Okay? Well, when you add, especially when you add matrices, think of this one as matrices, right? Think of them as matrices. If you're going to add matrix, their size must be the same. Yes? So it's the same with initial notation. So we have a first rank, a vector, should be added with a vector. You cannot add a vector and a scalar. You can only add a vector with a vector. That's addition. A second rank tensor with a second rank tensor. Okay? So these are the operations that are possible. You cannot add a vector and this one here. Okay? So these are the operations that you can have. So as you can see, those are addition of vector, addition of two rank or second rank tensors. This one is matrix. Symbolic matrix. This one will be initial notation. And this is the expanded matrix. So as you can see, it's more convenient to write in this manner rather than this manner here. Okay? So, economy as well as convenience. Contraction, later on we will be going with some examples, but at the moment, if we have dummy indices, so for example this one here, right, we have repeated indices. If you have repeated indices, the rank will be reduced by 2. So for example, I'm going to multiply this one here, contraction, right? This one is a tensor, ij, and this one is another tensor here, vector here. So as you can see, j here and j, they are repeated. So if you count the number of indices 1, 2, and 3, this one will be reduced by 2 orders, meaning 1, 2, 3 minus 2, so that the order here will be 1. Okay? So if you have repeated indices, you're multiplying tensors, and then you end up with repeated indices, that, okay, the total rank okay, what I'm saying here is that, say for example, I have a second order tensor. So let's say that you have a stress. So this will be my stress. Stress is a second order tensor. Okay? And then I multiply this one with a another tensor of order 1. Okay? So if I multiply them, dot multiplication, that is, if I multiply them, then as you can see, there are repeated indices j. So what will happen here is, you normally add the indices to determine the total rank of your tensor, say 1, 2, 3, but since you have repeated, okay, you have to reduce this one with 2. So that's 1, 2, 3, 3 minus 2, then you end up with 1. So meaning that here you will end up with this free index here, Ti. So Ti is equal to sigma I j multiplied by nj. So as you can see, this is a dummy variable. It can be any. I can change that to c, say sigma I k, and then I can have this one to be n k. But this one is dummy. So still I end up with a free index I. Dummy free. Okay? So try to digest. We'll have that. We'll have a lot of this one later. Not a lot, probably just a few. But anyway, I will be writing some of the equations more in initial notations. I will try to explain some also in using matrix. Yes. So that's basically the principle of contraction. So meaning is that you have, say for example, initially you have a huge tensors, a higher order rank tensors, you multiply it with another tensor. If there are dummy indices, then this one reduces by 2. So as you can see here, this epsilon ijk multiplied by this vector here, so j will be a dummy index. So at the end of the day, you come up with ik to be the free index. Dummy meaning I can have this one to be f, p, or whatever. So if this one is p, this should be p. Dummy index. So the result here will be that free index ik. You cannot repeat. Say for example here, j here, j here. If this one is j, then this one is already improperly represented. So you should have a maximum repetition of an index of 2. Okay? Should only be repeated twice. An index must only be repeated twice, maximum, for a single equation. Okay, so that's the meaning of contraction. So as you can see here, we have a vector ai, bi. As you can see, they are, it has a dummy index, ii. Yes, so 1, 2, that is 2 now. The order is supposed to be 2, but since these are repeated, so you reduce 2. So 2 minus 2, so the order now is 0. So as you can see here, this is now a scalar. Rank 0. Okay, so that's the principle of contraction. Yes, later we will also look into this one later for some of our examples. Kronecker delta is a second order tensor, Kronecker delta. We'll have an example of this one later. Okay, just remember that the value of a Kronecker delta is 1 or 0. Differentiation, of course, we can have this one to be simplified rather than writing it in this manner. Okay, you can have this v I comma j. That comma represents differentiation with respect to j. Yes, so similarly with this one ui comma j, which is the partial derivative of ui with respect to xj, and so on and so forth. Okay, so this comma here represents differentiation. So again, like I said, it's the convenience, economy, rather than writing it in this manner, you have to write it in this manner. Okay? And of course, you have the different types of multiplication, the dot product, the inner product, which is the contraction that we had already, outer product, dyadic, and the vector product, or the cross product, wherein the result will be a vector. So what we had earlier, the contraction is actually a dot product. Okay? And then we have the dyadic product, or the outer product, and then the cross product. Let's have a look. So we've done this one already. Okay? You are multiplying here two vectors. Yes? And then, of course, if you have a dot product, this is a simple, what do you call this one, a contraction. We'll have more on this one at the moment, just accept that dot multiplication is equivalent to contraction. This is the thing that I want you to know, delta ij. So delta ij is equal to 1 if I is equal to j. This one is 0 if I is not equal to j. So that's the value of Kronecker delta. We'll have a few exercises using Kronecker delta. So how do you represent this one? Let me see. So for example, how do we write that? So for example, I have now a matrix. Say this one is U1, U2, and U3. And then I have another one here, V. So let me bold that a bit. This one is V1, V2, and V3. Now, if I'm going to write this one as an initial notation, using initial notation, that is simply UI. So here, where I is equal to 1, 2, 3. So I can have U1, U2, U3, yes? And the same is true with this one, VI, where I have J equal to V1 or 1, 2, and 3. Okay? Now the good thing about this one, dot product. The dot product is basically going to have a reduction. Okay? So if you're going to multiply this one, you're looking at U, yes, transpose, let me bold that a bit, multiplied by that V. So this U transpose is going to be U1, U2, U3, and that will be V1, V2, V3. So you're going to end up with U1, V1, U2, V2, plus U3, V3, which is a scalar. So in initial notation, so I'm going to use UI, VI. Yes? So where I is equal to 1, 2, 3, this is a summation. I can write this one as sigma, or the summation, of UI, VI, where I is equal to 1, 2, 3. But what was observed before is that if you have this one here, repeated index, it's actually a summation. So to be able to further simplify, you just remove this one. Okay, that's the reason for that. Nothing scientific about this one. What was observed is that if you have the summation and repeated index, there's always a summation. So that's where the rule becomes, wherein if you have repeated index, you have a summation. So then you have U1, V1, plus U2, V2, plus U3, V3. So how do we write that? Let's put in some Kronecker delta. Let's make it more interesting. But, okay, remember, this one is Vj. So how can we write how can we write it again if we put in a Kronecker delta? Instead of using this one here, Vi, I use this V with the subscript J. Let's do that. Let's put in a Kronecker delta. Let's make it a bit more interesting. So I have UI, Vj. I have delta ij. So this is equal to 1 if I equal to j. And I have this one to be 0 if I is not equal to j. So how do we write that? So this one now will be ui bj multiplied by a Kronecker delta ij. Yeah? So as you can see, this one is 0 if I is not equal to j. Yes? This one is equal to 1 if I equal to j. Yes? So this is equal to 1 if I is equal to j. So how do we have a product here? So if I is not equal to j, this one becomes 0. Yes? So if I is equal to j, this one becomes 1. Yes? So there will be a value. So what will happen is that since I is equal to j, or since delta ij is equal to 1 if I is equal to j, then simply this one changes to I. Every time. It happened to me too when I was a student like you. So, okay. Let's go with numbers. 1, 2, 3. Let's go with numbers. I have now U1, let's start with 1. And then I have now V1, delta 1, 1. Yes? So as you can see, there's a summation here, but let's just have it with 1 first. Plus, there's a summation here, and then sum it more, and so on and so forth. So I have now U1 plus, multiplied by V2, and then what will be my Kronecker delta? So this one is delta 1, 2, which is 0. So this one is 1, okay? And this one is 0. Plus U1 V3 delta 1, 3, this one becomes 0, and the whole thing becomes 0. So what's left will be U1 V1, yes? Same is true. I have U2 V1 delta 2, 1, that becomes 0, plus U2 V2 delta 2, 2, plus U2 V3 delta 2, 3. Then again, you add this one to be U3 V1 delta 3, 1, and so on. U3 V2 delta 3, 2, and then you have U3 V3 delta 3, 3. So what do you have? So this one is 0, so that becomes 0. This one is equal to 1. This one becomes 0, 0, 0, and this one becomes 1. So this one ends up to be U1 V1 plus U2 V2, U3 V3. Yes? And then you end up again with UI VI. So UI Vj delta Ij is equal to UI Vi. So we proved that, yeah? Take note that if you have a repeated index, then there's a summation. There is a summation here, there's a summation there. Okay, so at the moment, just try to accept this one. But we were able to prove it anyway. Interesting. questions so far? So not yet sleepy? I have a lot of materials that will make you sleep. So let's wait. So that's what we have at the moment. Contraction, of course. The others are rather straightforward. Dot product, as you can see, you can reduce this one here. This one is the dot product, Tij, Aj. There's a repeated index there. So you end up with a single, a first order vector, or tensor, sorry. Okay? Dyadic tensor, dyadic product, this value actually increases the size or the rank of your tensor. We will be going through this one with some examples later if we ever encounter the need to. Outer product. We have vector product, we will have this discussion. So what's really important at the moment? The dot product and the vector product. Of course, we will have a few examples on the outer product. So this one is multiplying a vector with a vector. You end up with a vector. Take note of this one. There is a permutation symbol, epsilon ijk. So in addition to the Kronecker delta, you have a permutation symbol. So this can have a value of 1, -1, or 0. So if you want to represent it in a matrix form, this is how a vector product looks like. Okay? Vector product, if you multiply two vectors, that is the determinant of the two vectors, of this matrix. So U multiplied by V, assuming that it goes from 1 to 3. So you have U1, U2, U3, VI, V2, V3. Then you have your unit vectors. Take the determinant. This is now your vector product. Again, Kronecker delta. And then you have now your permutation symbol. This one is second order normally, and this one is a third order. Trace, you probably won't use much of that. Of course, try to look into the different operations, gradient of a scalar. This one is a del operator. Okay, partial derivatives, and then you have unit vector. So this one is a vector. Okay, and then the gradient is of course del multiplied by a scalar. So we're trying to, what are we doing here? We're just trying to define terms at the moment. Okay, and then we have the differential operators. You can have the gradient of a function. And then you can have the divergence of a vector. Okay, wherein you have this del operator multiplied by a vector field. Okay, so initially we have a del with a scalar that is called gradient. So we have now a del multiplied by a vector. This is called the divergence. Okay, so that is dot multiplication. And then finally, you have the curl of a vector. So a curl of a vector is a cross multiplication of two vectors. This is a vector, that is a vector. Cross multiply, then you get this one here. Okay? So the curl of a vector is the determinant of this matrix here. So you can have this example. It's posted in Moodle, so it should be there. Any questions so far? So actually we've gone through this one in Mechanics 3, so it's just a review, so try to go through them again. I know it's like, what? 8 months ago? Is that 8 months ago? No. 6 months ago, where you had this last topic of the Mechanics 3. Any questions so far before we proceed in a more interesting topic? So as you can see, we have finite elements, and you couple that with continuum mechanics. So this course basically covers, before you can even understand a lot of continuum mechanics principles, it's really important. It's really important that you have a good understanding in tensors. Tensors is an introduction to continuum mechanics. Once you understand continuum mechanics, it will be easier to apply finite element method. Okay? So what we did in Mechanics 3 is just a simple strength of materials, couple that with simple finite elements analysis, skeletal. All of them are so straightforward, but this one, I think we have to do a lot of mathematics and physics. Any questions so far? So I will be summarizing what to expect from continuum mechanics. And then after that, starting next week, I will be giving the details. Reason, of course, I want to present what you need or what you should be expecting from this course. Okay? Are there any failures? No, not really. Exams are easy. Okay. Tips to pass, of course. Study. Do your report. Of course, that will also be helpful, the peer-wise. Enrollment code for the Moodle. I would think you already have been enrolled. Not yet. I think it's automatic. So anyway, if that's the case, then I'll send you the enrollment code. I would think it's already automatic when you start the semester.
Jessica, never do her job.
Yes. Questions before we move on? So the first part of this continuum mechanics is just trying to go back to what you know in strength of materials. So you probably have taken strength of materials in your poly. We did a bit of strength of materials in Mechanics 3, and then we're going to go back again to that introduction. And from there, we're going to move on. Okay? So I'm going to present a few of this continuum mechanics principles, but we have to review a bit. So as you can see, you probably won't be able to get too much from this one, but I'm going to give you an overview on what to expect from this course. One, of course, will be that theory of elasticity. Why in the world do we have elasticity, and where did that theory come from? And then we have the theory of plasticity.
Korean 最厉害了。
Okay, mechanical properties. You probably have been, well, of course you're mechanical engineer, so you should have already had courses in materials. So of course you know the importance of material properties. Before you even do a design, you should also be able to come up with your materials definition. When you come up with your geometry definition, that's the size, the shape, dimensions, and so on, then you also have to identify the different materials that you have to do. Okay? So I would think you have already undergone the CES software. But sometimes students overdo the use of, or overdo the use of the CAS software. If they're going to choose among 3 materials, some students will still use the CES software. Why is that so? Okay, just for the beautiful pictures, isn't it? But you see, that's not the purpose. Unless, of course, you have like 5 or 6 materials and so on, where you want to choose which material is the best, then you probably have to use the CES software. But if you're just choosing from 2 or 3 materials, then using the CES software doesn't make sense anymore.
Why?
Yes. So,
In this one.
from different perspectives, we have different interests. For design, elastic modulus. Okay, so these elastic modulus are actually given, and then we come up with the yield strength. I'll show you the figure later for the stress strain curve. So they are important in order to resist permanent deformation under applied stresses. The focus is on the elastic properties. That's from the point of view of the designer. You don't want to exceed the strength of your material. Okay, when you design something, you load something, you calculate the stress, you ensure yourself as a designer that the strength must not be greater than, or the stress must not be greater than the strength of the material. That's design, isn't it? Okay, because if the stress acting on your material is greater than its strength, then definitely it's going to fail. Common sense. So in manufacturing, the goal is to apply stresses that exceed the yield strength of the material so as to deform it to the required shape. So the focus is on the plastic properties. Elasticity, plasticity. So where does this come from in the first place? Elastic, we don't want to limit, we don't want to exceed the strength or the stress acting on our material to that of its strength. However, in manufacturing, we would like to exceed that yield strength so that we can be able to deform that material. Elasticity, plasticity. So, different point of views, but two very important things for engineering and manufacturing, that is. You have seen this one, probably? Tensile testing? Yes? So what does it do? What does it give? If I'm going to test a material, whether it's plastic, metals, aluminum, iron, steel, whatsoever, what does it give out? Yield strength? Specifically, yield strength. What else? Stress strain curve, yes? So we get the stress strain curve from this tensile testing. Okay? For different materials, we test them, we get the SN curve. Oh, sorry, the stress strain curve. And what can we get from the stress strain curve? So we do this one, it's a simple basic principle until it fails and so on. You get your stress strain diagram or stress strain curve. Okay, so you got your stress strain curve. So where is plasticity? Where is elasticity here? Theory of elasticity. Linear elastic. So from the tensile test, we did a lot of testing, so on and so forth. We choose our material. End of the day, we come up with a stress strain curve. So it can be through stress, through strain, whatever, we don't care at the moment. So that is my stress strain curve. Now there is a location here, okay, a part here, wherein it's linear. Yes? Or maybe exceed a bit here or so on and so forth. Maybe let's exceed a bit. Okay, so as you can see, it's linear. So once you stretch a material, and then you reach this one, and then you release it, it goes back to its original shape. Okay, meaning it's going back, elastic, like a rubber band. But once you exceed that limit here, once you exceed this limit here, then chances are that elongation will be permanent, plastic. Okay, but once you're in this limit here, just before that, just before this one here, okay, so you're looking at elastic, meaning it's going to go back to its original shape. And it's linear, really. Exceeding this one, going there, it becomes plastic. So we have an elastic region, and then we have from here until it fails, you have a plastic region. So here applies the theory of elasticity, and here applies the theory of plasticity. Okay? So where does modulus comes in? Where does Young's modulus comes in? Now have a look at this one here. That is linear, meaning that your stress will be proportional with your strain. So that in order to equate this one, you must have a proportionality constant K. And that proportionality constant is your modulus. Yes? Stress equal to your modulus multiplied by your strain. So this constitutive equation, meaning it defines the behavior of your material, was derived from test, from this linear or linear elastic region. So stress is proportional with strain. To be able to equate it, you need a proportionality constant, and that proportionality constant is actually Young's modulus. Yeah? And this is, of course, the Hooke's law. Yeah? So this is the Hooke's law, or your constitutive equation. Stress equal to your modulus multiplied by your strain. Now, of course, that is just 1D. Again, if you want to expand it, you can have a 3D if you want to. Not a problem. That will be more interesting, really. And of course, there will be some assumptions to that. Now, let's go back. Yes, here we go. We have now the stress strain diagrams, which is a plot of stress versus strain for a given material. So your tensile test will be giving out this one here. Linear elastic region, which is this one here. Okay. So normally you get the yield here, and this is your ultimate, and then this is your when your material fractures. This is your ultimate strength, where you can have the maximum load. So this area here is your plastic region, while this area here is your elastic region. Linear elastic region. Region in the stress strain diagram where stress is generally proportional to strain. Non-linear plastic region. Region in the stress strain diagram where the stress is not proportional to strain. Those are definitions. Now, for different materials, you have different behavior of the stress strain curve. So mild steel, iron, and so on. You have this different types of stress strain diagram. Okay. Don't worry. I will be sending you the key or the password or the PIN to that Moodle 4M, Mechanics 4M. That is. So again, this one just describes the how you were able to get the ultimate strength and so on. You have engineering versus true strain. Probably have done this one already. Very basic. We're just going back to the basics at the moment. And then some of the things that you need to know. Before I continue with this one, let's have a 10 minutes break.
Oh, yes.